And our next guest speaker, Dmitriy Setrakyan, he's a special guest. You know what? I will describe Dmitry in these three kind of short sentences. First, as a co-founder of GridGain, Dmitry was among the few who were writing the first lines of the code of the project that would become Apache Ignite. Next, at the first Ignite PMC chair, Dmitry was helping the Ignite community to grow during his first years. And right now, as a senior manager at Amazon Aurora, he is building, designing, and running in production some of the most complex and sophisticated cloud-native and serverless databases. So join me in welcoming Dmitry, and let's learn from Dmitry today.
Thanks for the warm introduction. Yes, I did write some initial code for Ignite. In case, hello Igniters. Thanks for joining. Again, I'm Dmitriy Setrakyan. I'm working as a senior manager at AWS Aurora MySQL. I'm mostly focused on working on serverless offerings for Aurora. It's an honor to be here. It's an honor to be able to open Apache Ignite Summit for America. I've been with Ignite from the very early days. I've been with GridGain when we donated the source code to Apache. I've been there when we were working hard on driving it through incubation process, and I remember how happy we all were when it finally graduated to the top-level Apache project. And it's very exciting to see how the project grew over the years, how it got here from where it was back there to become one of the most thriving, most active communities and developer communities and most active user bases in Apache Software Foundation. So we definitely couldn't have done it without you, and you should all be very proud. So thank you. So today we are going to be talking about the future of elastic databases. But before we actually start defining what an ideal elastic database should look like, let's try to categorize, let's try to step back and categorize the existing databases as we know them. And the first and biggest category that we all know is SQL. Here we're talking about a relational database management system, databases like Oracle, MySQL, Postgres, some distributed cloud offerings like Amazon Aurora, AWS Aurora, like Google Spanner, all would fit here. And these databases usually have several properties that are common across all of them. One is they're strongly typed. The schema is strong, every data type is strongly defined. Another is they're fully consistent, strongly consistent. And the reason these RDBMS systems are strongly consistent has to do a little bit with history, I believe. If you remember that as the database industry was evolving, for a very long time, RDBMS systems were still deployed on a single database server. And it turns out that implementing consistency on a single server is much easier. It's not easy, but it's much easier than implementing consistency across a distributed system across multiple servers. Even back in the days when we started moving to distributed architectures, like I think they were called 3-tier architectures, and we were distributing the workloads across multiple web servers, and we were distributing application logic across multiple app servers, we were still storing data in a single database server. And that's where strong consistency probably was rooted in and then actually evolved to where we are today. But about a decade ago, a single server could not scale anymore. With the emergence of big data, we couldn't scale vertically fast enough. And that's what gave birth to the new family of databases, which is now we know as NoSQL databases. There are two main types of NoSQL databases that I'm going to mention. One is key value, and another is document databases. For key value databases, think databases like AWS DynamoDB, probably Elasticache, Redis, Ignite does also fit in this use case. So the main premise of this use case is the data is accessed by key. So we store data by the key, and we retrieve data by the key. And because of that, we can actually scale out horizontally with relative ease, because we can just assign a certain key set or a certain data set, and then whenever we need to update that key, a key with that key set will go to that server. If we have a lot of data, the more servers we add, the more keys we can access in that sense. So key value databases scale out horizontally pretty well, and they're generally used for use cases when we need very fast access by way of key lookup across a very large data set. So another type of databases that I want to mention is document databases, and those databases emerged with the introduction of Web 2.0. All of a sudden, we have big data. All of a sudden, we have large amounts of unstructured data, mostly coming at us in JSON formats that we need to store, we need to query, and that gave birth to the document databases like Mongo, like Couch, AWS DocumentDB also plays there. So those databases are there to support this use case. There are also many other categories. I will call them special purpose databases. We have graph database for a highly connected use case. We have time series database for querying data within periods of time. We have analytics database that can execute very complex queries on very large read-only data sets. But there's also one category that I didn't mention, which is a memory category. And here I want to pause a little bit, because memory category, I believe, is a little bit has evolved over time. And I believe today we have two main types of in-memory databases. One is the databases or caches that uses memory just to store data. So essentially, these caches, these databases are the main purpose is to reduce latency and provide sub-microsecond latencies by accessing data in memory. You can also have some fancy data structures, like, for example, sorted set and Redis, etc., that could actually facilitate a certain use case with a fast and memory access. Databases, so essentially the main purpose here is to provide very fast microsecond and below access to the data that is stored in memory. These databases are usually distributed across multiple servers, so they scale out very well, and they're also persistent. We're no longer having the days where if you hear in-memory database, that means if all your servers all of a sudden go down, you lose your data. Most of the in-memory database offerings are persistent, and in this way, they act very similar to the more traditional database offerings that I already talked about. So another memory category that I believe Ignite plays very well in is memory first. And the main difference of memory first databases versus a plain in-memory databases is that memory is used now not only for data, but also for compute. And this kind of architectural principle was put into Ignite from the get-go, and that's why Ignite actually plays very well with the use cases where you have to collocate compute and data. And the main reason why you want to do that is to minimize the data movement between cluster nodes. Moving data and having network hubs on your data access path is probably one of the most expensive operations a distributed system can do. And if you can minimize it, the less network hubs you can achieve, the better the performance you will get. And just imagine a use case where you have maybe 10 queries, could be SQL queries, could be simple key value or JSON access a JSON object. When you query, you come back, you do some processing, you query again, you come back, you do some processing. So even though the data access would still be fast, the data is still accessed from memory, you still have to make 10 network hubs, which will slow you down. With Ignite, it's possible to do that in one round trip, because now you can take all that compute logic and send it to one or actually multiple servers in parallel to compute directly on the nodes where the data is. And that's why Ignite is very fast. And that's why it's one of the, in my view, one of the fastest modern databases out there. So, of course, how can we talk about distributed systems if we do not mention CAP theorem? Basically, just a quick recap, CAP theorem is based on the premise that databases can support consistency, availability, and partition tolerance, and network partition tolerance, and any database can support only 2 out of 3. So where on the CAP theorem should a cloud database be? And here I would like to refer to the paper written by VP of Engineering from Google, Eric Brewer, called Spanner, TrueTime, and the CAP theorem. And there, Eric Brewer actually claims that Spanner is effectively a distributed SQL database. So as we talked about, it has to be strongly consistent. So Spanner is CP, consistent and network partition tolerant mainly. But Eric Brewer also makes a claim that if, from a user standpoint, that you can get your database failures, your network failures, to the point where they're negligible, when users do not even notice them, then you become effectively available. And the way they arrive to this term effectively available is by analyzing all the crashes that happen on Spanner. And it turns out that network partitioning plays a very small role in contributing to overall set of crashes that Spanner can go through. About over 50% of them, of the crashes, are user-induced, essentially what we call software bugs. Those crashes do happen. They happen on user clusters. They may bring out one cluster at a time, but they do not cause availability problems for the Spanner overall. The same goes for maybe crashes that happen within a single region, or crashes that have to do with hardware failures, etc., or software bugs within Spanner. Those may bring down a certain region, but overall the Spanner, since it's deployed globally, overall the availability of Spanner is still not impacted much. And there's only about 7.6%, that green piece of the pie chart, that has to do with network failures. And out of them, even smaller piece is responsible for network partitioning. And the reason for that, according to Eric, is the years of operational experience that Google has put into constructing its network. There's a lot of redundancy that is built into cloud providers' network to ensure that the network partitioning happens as rarely as possible. And effectively, if you can achieve 5 nines and above of availability, then from a user standpoint, the database is effectively available. And Eric Brewer claims that Spanner users don't even handle Spanner failures in their code. So that's how confident they are in the uptime of Spanner. So that's what, in my view, availability or uptime for a cloud database should be. It should be CP, and it should be effectively available. It should be consistent, partition tolerant, and effectively available. So now let's try to define what an elastic database is, and let's try to do it from a customer standpoint. Let's try to do what a customer. Let's try to look at what a customer would ask for when trying to create a database on the cloud. Well, number one use case is the customers want to store data. What customers do not want to do is predict in advance how much data they are going to store. They do not want to pay for the overhead. For example, if you want to store a terabyte, doesn't mean you're going to have a terabyte from day 0. So why should you pay for it from day 0, right? So they do not want to pay for the overhead. They want to pay for as much data as they use, but at the same time, they want to be able to use as much data as possible. They do not want to have any limits. They do not want to run out of space or run out of compute power. So let's call that that type of database limitless. Another property that is important to customers is scale. Essentially, what scale means is that there's no performance penalty for growth, right? So the underlying cloud database needs to be able to scale horizontally by splitting and by partitioning the data and sharding it. This way, you can actually achieve parallel processing on the data if there are parallel requests going across multiple shards. But that's only one aspect of it. a cloud database should also be able to scale vertically and transparently. It should be able to resize all its internal data structures if the load increases. For example, what if you have a hot partition that all of a sudden receives a lot of load, and now you need to increase your CPU capacity, you need to increase your memory capacity so you can do more caching, you need to increase your storage capacity as well. So a vertical scale that is transparent to the user is very important, and that is what we call today a serverless database. So again, we have to be limitless, serverless, and uptime is also very important. As we already discussed, cloud databases have to be consistent, partition tolerant, and effectively available, which means that over 5 nines availability. Cloud databases have to be secure. Users do not want to worry about security. There historically been two types of deployments on the cloud. One is when you let the user install their own database and install their own plugins, configurations, and break it as much as they want, and then fix it themselves. That's not what cloud users want. The cloud users want a managed service offering, where a cloud provider would automatically manage all the security, automatically apply the latest patches, be that kernel patches or CVEs for the database, or certify all the plugins to be secure, etc. So database has to be secure. And finally, cost. You do not want to pay for what you do not use. As your data set grows, you should be paying only for the data set that is being used at this point of time. The same goes for compute capacity, and the same goes for memory capacity. So memory and compute, as I mentioned, also should be able to size up and down. If, for example, you have a workload burst, you should only be paying for the burst, for whatever you're using during the burst. As the burst subsides, your database, you should only be paying for, again, the subsided workload that is there. Moreover, if there is no workload, the database should be able to scale down to zero, essentially going into sleep or hibernation state. And at that point, you should only be paying for storage because you are not using any compute and you are not using any memory at that point. So you want to pay for what you use. So these properties actually would, in my view, define the ideal elastic database. And it has to be limitless, it has to be serverless, it has to be consistent, partition tolerant, and effectively available. It has to be secure, and you should only be paying for what you use, and you should not be paying for what you do not use. So with that, I will conclude my presentation. Thank you for listening. Please do attend other talks. There's plenty of interesting talks that are happening today. And you can always reach me on Twitter or via LinkedIn. Just send me a message and I will respond as soon as I can. Thanks again.
That's great. Thank you very much, Dmitry. Really fascinating talk. Looks like we've got future is going to be great, the way things are going.